Someone in the other class pointed out to me that I had project 2 and project 3 due back-to-back to each other on 2 consecutive classes, because that just happened because of the snow days and stuff. So I changed the due dates a little bit. So it used to be project 2 was due here and project 3 was due here. So I just moved project 2 back a day and moved project 3 back a week. So I'll print this for you for next class, so you'll have the most up-to-date version. But it's already posted in Moodle, so you can print it there if you want it right away. Okay, so the first page of this packet is a reference sheet that you can use on the tests. It is a reference sheet about partial fractions and trig substitutions, and that is what we're going to talk about today. So this reference sheet pertains to the first lesson of the packet. Okay, so we're going to learn 2 new techniques for finding antiderivatives, finding integrals, algebraic identities or partial fractions, and trig substitutions. Okay. So these are techniques that very few people like. Prior to today, we blindly resorted to using a table of integrals for problems like these. But today we're going to be able to learn how to do them without a table. Yay! So I started, it was this class, I started using partial fractions to solve that integral that took me like 20 minutes and I was doing it all wrong. So today we're going to learn that technique that I was trying to do, partial fractions. Okay, so if I want to find the integral of 5x minus 10 over x squared minus 3x minus 4 dx, I could use the table, right? Because that's a linear over a factorable quadratic. So I could just use a table. But the whole point of today is to learn how to do this without the table. Okay. So the idea behind partial fractions is to take a complicated looking fraction and rewrite it as the sum of 2 simpler fractions. So I would like to take 5x minus 10, and that denominator factored would be x minus 4, x plus 1. So that's my fraction. I would like to rewrite it as a sum of 2 simpler fractions. Preferably fractions that would be easy to take an antiderivative of, right? So then I could take the antiderivative of each fraction separately and add them together. All right, so the denominator is going to be the clue about what this decomposition is going to look like. That's what they call this, partial fraction decomposition. All right, so if I have one factor will be one of my denominators and the other factor will be my other one. Okay, so if I was going to add 2 fractions together that have different denominators, I would need to get a common denominator first, right? Which means that this fraction that has an x minus 4 on the bottom, I'd have to multiply by x plus 1 over x plus 1. And this one I'd have to multiply by x minus 4 over x minus 4. Which means I'm going to have some x's in my numerator on each of these once I get a common denominator. So I don't want to add any x's, right? So just getting the common denominator is going to make my numerators linear. So I only want maybe some constants in the numerator. And then the question is, I just got to figure out what a and b I can use to make this statement true. This is what I would like to do. I'd like to take my fraction, it's a linear over a quadratic, and write it as a sum of a constant over a linear plus a constant over a linear. All right, so to figure out what a and b is, I'm going to use an old technique that we learned in probably college algebra to clear all the fractions from an equation by multiplying both sides by the common denominator. So multiply both sides of this equation by x minus 4 times x plus 1. Okay, so let's work on the right first. I have to distribute this x minus 4 times x plus 1 to both terms in the pink brackets there, to both fractions. So when I multiply this common denominator, x minus 4 times x plus 1, times the a fraction, the x minus 4s are going to cancel, and I'm going to be left with a times x plus 1. And when I multiply this common denominator times the fraction with the b on top, the x plus 1s are going to cancel, and I'll be left with b times x minus 4. And on the left, x minus 4 times x plus 1 is going to cancel with the whole denominator, so I'm just left with 5x minus 10. Okay, so now I still have two unknowns. Well, technically 3 because of the x, right? So I still have, well, x is a variable. So a and b are my unknowns. I have two unknowns. Usually you need two equations. If you have two unknowns, you need two equations, right? But I'm going to use a really tricky little sneaky thing by matching up the coefficients. Okay. So I'm going to distribute and combine like terms on the right. And then I'm going to have something linear on the right and something linear on the left. So I know that the coefficients on x have to match and the constant terms have to match. So when I distribute here, I get ax plus a. And when I distribute here, I get bx minus 4b. Combine like terms, so I've got an ax and a bx. And I've got a plus a and a minus 4b. So ax plus bx, combine those like terms, and you have a plus b times x. And then a minus 4b, that's going to be my constant term. So I'm just putting parentheses around it to say, like, this is a whole term, just a constant. And that has to equal 5x minus 10. All right, so now I can match up. The 5 is a coefficient on x on the left. That has to be the same thing as the coefficient of x on the right. So 5 has to equal a plus b. These have to be the same. And my constant term, negative 10, has to equal that constant term in order for the left and right to be equal. There's no other way to make them equal. All right, so over here, I'm going to write 5 has to equal a plus b, and negative 10 has to equal a minus 4b. Now we have two equations with two unknowns. So now we can solve for a and b. So you can use your favorite technique. You can use substitution. You can use elimination. What do you want to do? Substitution? All right, so maybe I'll start with this equation, and I would say a is equal to 5 minus b. So then you go to your other equation, and you replace a with a 5 minus b. That's the substitution piece. So I've got negative 10 is equal to 5 minus b minus 4b. And now I can solve this one for b. So negative 10 equals 5 minus 5b. Subtract 5 from both sides. Oops. So we get minus 5b. So b has to be 3, which means that a has to be 5 minus 3, which is 2. Okay, so we've done the decomposition, but we haven't answered the question, right? The question was, find the integral of this thing. All I've done so far is rewrite the integrand as a sum of two simpler fractions. So let's put this on a new page. Okay, so now I can rewrite my integrand as a sum of two simpler fractions, right? It's going to be something over, how did I break it up? X minus 4 was first, okay. Plus something over x plus 1 dx. And this was a and this was b, which I have now solved, and I have 2 and 5. Okay, so I can rewrite that as two separate integrals, right? When you take the integral of a sum, you can take the integral of each piece separately. So this is the integral of 2 over x minus 4 dx plus the integral of 5 over x plus 1 dx. All right, so what do you think? What should we do now? I could pull the 2 and the 5 out, yep. Was it 3? Oh yeah, thank you. Just seeing if you were paying attention. Good job. Okay, now what? How do I find those two integrals of 1 over some stuff? I could use a u substitution, right? What would you let u be? Yeah, x minus 4 and the x and or the x plus 1. Yep. So this would end up being like a 1 over u, and the antiderivative of 1 over u is ln absolute value of u. Okay. So for this guy, let's say u is going to be x minus 4, which means that du dx is 1, right? So dx equals du. And then in this guy, we should probably use a different variable because the u's will be different. So I should not use the same letter to represent a different thing. So maybe I'll use w. This one will be x plus 1. And so dw dx, again, is just 1, which means that dx equals dw. All right, so this is 2 times the integral of 1 over u du plus 3 times the integral of 1 over w dw. And I know the antiderivatives of 1 over something, right? It's ln. So this is going to become 2 ln absolute u plus 3 ln absolute w, and then a plus c. Technically, these two integrals each have their own plus c, but because c is arbitrary and can take on an infinite number of values, I'm just going to smush them into 1 plus c. And then I should replace my u and my w. So this is 2 ln x minus 4 plus 3 ln x plus 1 plus c. Okay, so the trick to being able to do this problem without a table was the partial fraction decomposition. Okay, so the form that a partial fraction decomposition is going to take depends on the factored form of the denominator. Okay, so in the last one, we had simple, non-repeated linear factors. Okay? Anytime you have a non-repeated linear factor, You just use that as a denominator of one of your sum fractions with a constant on top. Okay? That's what this first term says. For each factor that looks like x minus c, you should include in the partial fraction decomposition a constant over that factor. If you have a repeated linear factor, so if you had like x minus 4 squared, right, you would have to use that linear factor twice. Well, 3 times. You put a constant over it by itself and then a constant over it squared. If it was cubed, you'd have another constant over it cubed. And then if you have an irreducible quadratic, right, something that can't factor without the use of i's, then you put a linear term over that quadratic term. You should first use polynomial long division if the degree of the numerator is greater than or equal to the degree of the denominator. So here's an example that involves partial fractions of all 3 types. I've got 1 over x minus 1 times x plus 1 squared times x squared plus 4. So this factor tells me I need a constant over x minus 1, right? A non-repeated linear factor. All right, then I have a repeated linear factor. I have an x plus 1 squared. So I need a constant over x plus 1, and then another constant over x plus 1 squared. If that was cubed, I would need another constant over x plus 1 cubed. And then I have an irreducible quadratic, x squared plus 4. You can't factor that without using i's. So I need a linear term over the x squared plus 4. Dx plus e, a linear term where I don't know the coefficient on x or the constant. Okay, so let's try a few more. I want to find the integral of x squared over x minus 3 times x minus 1 times x plus 2. Okay, so over here, I think I'll do the partial fraction decomposition. See if I have enough room. Gave myself enough room there. All right, so x squared over x minus 3, x minus 1, x plus 2. All right, what kind of denominators do I have? Linear, non-repeated, yeah. So I just have to put a constant over each one of them. So I'll have a over x minus 3 plus b over x minus 1 plus c over x plus 2. Yeah, I'm definitely going to need more room than that. Okay, so the way I start this is I have to multiply both sides of my equation, every term on both sides, by the common denominator. I'm going to try to clear this equation of fractions. So I multiply this side by x minus 3, x minus 1, x plus 2, and multiply this side by x minus 3, x minus 1, x plus 2. So the left side, the whole denominator cancels with what I'm multiplying by, and all I'm left with is an x squared. And then on the right, I have to distribute this common denominator to all 3 fractions. When I distribute it to the fraction with an a on top, the x minus 3's are going to cancel, and I'm left with a times x minus 1 times x plus 2. Then distribute the common denominator to the fraction with the b on top, and when I do that, my x minus 1's are going to cancel. And I'm going to have b times x minus 3 times x plus 2. Then distribute it to the c fraction, and the x plus 2's are going to cancel, and you have c times the other 2, x minus 3, x minus 1. Okay, so I'm going to let you do a little bit of this algebra. I want you to multiply everything out and combine your like terms. Okay, so everything multiplied out. First thing I did was FOIL my binomials. You don't have to do that first. So I saw some people were distributing the a to the first term first. So you have ax minus a, then times x plus 2, and then you could FOIL those two things out. You get the same thing. Okay, so first thing I did was FOIL those three guys. Then I distributed my a and my b and my c. And then I collected like terms. I said, oh, look, I've got an ax squared, a bx squared, and a cx squared. Combine those into a plus b plus c times x squared. Then I collected my x terms. I've got a plus ax minus bx minus 4cx. So my coefficients are a minus b minus 4c, all times x. And then I collect my constant terms. Minus 2a minus 6b plus 3c. And I just put them all together. That's my constant term. All right, so now I'm going to equate coefficients. So on the left, my coefficients are 1, 0, and 0. 1x squared, 0x plus 0. So a plus b plus c has to be 1, because the x squared coefficients have to be the same. The x coefficients have to be the same, so a minus b minus 4c has to be 0. And my constant terms have to be the same. Negative 2a minus 6b plus 3c has to be 0. All right, so I have 3 equations, 3 unknowns. I should be able to solve this if I just put in enough time and energy, right? Okay, so I can use substitution or elimination, leaning towards elimination because I'm hoping I could get rid of more than one variable in one shot here. But it's not always possible. In fact, I don't think it will be. All right, so I'm going to take this a plus b plus c equals 1 equation and write it underneath the a minus b minus 4c equation. And add them together. Why am I doing that? I'm going to eliminate the b's. Yeah, I have a negative b and a positive b. Add them, they're going to go away. So I'm going to have 2a and then minus 3c equals 1. All right, so I've got an equation with just 2 variables. If I could get another equation with just 2 variables, I could solve that using a standard technique. Any ideas? Put the a plus b plus c, or under which one? Put a plus b plus c here. Oh, the 2a minus 3c. Oh, yeah, because look, I have a minus 3c there and a plus 3c here. Great. And minus 2a. Good. 2a minus 3c equals 1. Add those together. 2a's drop out. I have minus 6b. The 3c's drop out. Equals 1. Divide both sides by 6, and we get b is negative 1/6. All right, now what? Okay, so 2a equals 1 plus 3c. Substitute that in here. And the b and solve for the c. Good. Okay, I should finish solving for a here. 1 plus 3c over 2. Okay, so now I have an equation with just c's in it. So I'm just going to multiply everything on both sides by 6. I'm going to clear the equations, the denominators. So I'm going to end up with 3 plus 9c minus 1 plus c equals 1. So I've got 10c and, oh yeah, thank you. Thanks. 10c, and 3 minus 1 is 2, 6 minus 2 is 4. So c equals 4/10 or 2/5. And then I can go back to my a equals equation, plug in the c, and I'll have that. 1 plus 3 times 2/5 is 6/5. 5/5 plus 6/5 is 11/5. Times a half is 11/10. Did I do that right in my head? 11/5 divided by 2 is 11/10, yeah. All right, so I have values for a, b, and c. This is only the preliminary work to being able to solve the integral, right? All right, so a is 11/10. Go back to my integral. I can rewrite this now as the integral of 11/10 over x minus 3 plus the integral of b, which was negative 1/6. Yeah. Negative 1/6 over x minus 1 plus the integral, oops, I forgot my dx's, of 2/5 over x plus 2 dx. Then they can take each of those numerators as constants and just pull them right out of the integral. Minus 1/6, the integral of 1 over x minus 1 plus 2/5, the integral of 1 over x plus 2. And then I could write down the u substitution, but because if I was in this first example, right, if u was x minus 3, du dx would be 1. So the substitution is very straightforward. So I'm just going to not write it down, but you can if you want. So this is going to be 11/10 times the ln of the absolute value of x minus 3 minus 1/6 times the ln of x minus 1 plus 2/5 the ln of x plus 2 plus c. Is that okay? So most of our work in finding this integral was just algebra. Just a ton of algebra trying to simplify the fraction that they gave us, or to break it into a sum of simpler fractions. All right, why don't you try B? Okay, so this is going to factor to a one linear factor and an irreducible quadratic factor. So you have to use that form. Okay, so here's the form of the decomposition. The factored form of the denominator is x times x squared plus 9. X is a linear factor, so you just put a constant over it. Right? And x squared plus 9 is an irreducible quadratic, so we have to put a linear term on top of it, vx plus c. All right, so then just ignore these integrals. We're just doing the decomposition right now. I'm going to multiply every term on both sides by the common denominator. Ignore that. Okay, so on the left, the whole denominators cancel. I have 2x squared plus 4x minus 9. And on the right, when I do the first term, the x's cancel, and I have a times x squared plus 9. And the next term, bx plus c over x squared plus 9, the x squared plus 9's cancel, and you end up with bx plus c times x. Okay, so now I distribute everything and combine like terms on the right. So I'm going to have an ax squared plus a bx squared. So I have a plus b times x squared. And then 9a, that's going to be a constant. So I'm going to save that till the end. And I have a cx. That's going to be my only x term. And then my constant is going to be 9a. And that's my only constant term. So that should equal 2x squared plus 4x minus 9. Set the coefficients equal. So the coefficient on x squared on the left and the right have to be the same. 2 equals a plus b. 4 equals c. And negative 9 equals 9a. So I know c, that's good. And I know a has to be negative 1. And then b would have to be 3. All right, so I got my 3 constants, negative 1, b, negative 1, 3, and c. Negative 1, 3, and 4. Having trouble differentiating letters and numbers. Okay, so we go back to the integral that we're trying to solve, and I put in what a, b, and c are. And I'm going to separate them into 2 separate integrals here. B was negative 3. C was 4. D is positive 3. Okay, so this first integral, I can pull the negative out. I can't really pull anything out of the next one because there's no common factor to 3x and 4 that I could just pull out. So I'm just going to leave it. All right, so this first one is easy. This is negative ln x. But how do I do that? Right, so the whole thing with by parts is that when you have a non-reducible quadratic in the denominator, you put a linear term over it. We already have that, right? So there's nothing we can do with partial fractions. Oh, sorry, I thought you said partial fractions. You said by parts. Okay, so we can't do partial fractions, right? By parts, interesting idea. I'm not going to pursue it because I know it won't work. So for now, right, the only thing we know how to use to do this is the table. Okay, you go to the table, or you could wait 10 minutes and you'll know how to do it. Okay, so this we can't really do yet unless we resort to the table. A few minutes we'll know how to do it. Okay, let's just set this one up, not actually solve it. We'll just set up the decomposition. Right, so that numerator will factor. I could pull out a 5x, I'm sorry, a 2x, and I'd be left with 5x. I'd be left with 5 minus x, right? So nothing cancels if I reduce that, if I factor that numerator. So that's just what you want to check for. See, get anything to cancel that can cancel first, but nothing will cancel. So I'm going to have to rewrite this as my x plus 3, that's a non-repeated linear factor, so it gets just a constant. And then I have a repeated linear factor, so I put a constant over the factor by itself, and another constant over the factor squared. If that x minus 1 were cubed, I would add another term with a d over x minus 1 cubed. So that is how you would do the decomposition there. Yes.
Could you do the x minus 1s first, or do you have to have that a?
No, you could do the x minus 1s first. Yeah, that's fine. Yeah, because you can do addition in any order. So your a and my a would be different numbers, but when you put it back in, you know, once you solve for a, I would put that number over x plus 3, and you would put that number over x minus 1. So in the end, it will all come up the same. Sorry, there's one more on there. There we go. Okay. So let's set up one more partial fraction decomposition for a ridiculous example that would take you a really long time. So I've got 1 over x minus 2 times x plus 4 cubed times x squared plus 9. So I have a non-repeated linear factor, a linear factor repeated 3 times, and an irreducible quadratic. Okay, so my linear factor, non-repeated linear factor, just gets a constant over it. My repeated linear factor, I have to have as many terms for that repeated linear factor as it is repeated. Right, so I'm going to put a constant over x plus 4, another constant over x plus 4 squared, and another constant over x plus 4 cubed. And if that were x plus 4 to the 4th, I would have plus another constant over x plus 4 to the 4th. And then finally, I have an irreducible quadratic, so I have put a linear term on top, ex plus f over x squared plus 9. You would do the exact same procedure you did before, clear the fractions, multiply, distribute, combine like terms, and then you would end up having to equate 6 coefficients. You'd have 6 equations and 6 unknowns. I'm not going to ask you to do this, just wanted to show you how to set it up. So you could see all the different types of decomposition. Okay, the general procedure for partial fractions is on page 1 of the packet, and you can bring that with you to a test. Shows you all the different types of decomposition. Okay, why can't I use partial fractions on these two? What do the denominators have in common? They don't factor, right? Yeah, neither of them will factor without using an I. You can't get these to factor. How can you tell x squared plus 2x minus 8 doesn't factor? You try to factor it and you can't? Yeah, you can do that, or you can check, you can always check b squared minus 4ac. That's the thing that's under the radical in the quadratic formula, b squared minus 4ac. If that comes out negative, you know you can't factor it because it doesn't have any real solutions. So b squared minus 4 times a times c. Yeah, 4 times a times c. Oh, I guess it can factor. It does. I probably could use partial fractions on that. Why couldn't I? I think I could. But the second one does not factor. The denominator does not factor, right? This is an irreducible quadratic. And so partial fractions would tell me if you have an irreducible quadratic factor, you put a linear term on top of it, but I already have that, right? This is already a linear over an irreducible quadratic. So partial fractions can't get me any further. So yeah, so I can't use partial fractions on that one. It's just not going to help. It's not going to do anything. So for A, I don't know. I don't know why that's there. Maybe it's supposed to be a +8. Does that make it unfactorable? Yeah, if it was a +8, it would be an irreducible quadratic, and then it would be a linear over an irreducible quadratic. So again, linear over irreducible quadratic. Partial fractions can't help me. So in a case like this, you use something called a trig substitution. So when you have an integral that you want to simplify that involves an a squared plus or minus an x squared, you can make a trig substitution. So let's find the integral of 1 over radical 9 minus x squared. Okay, so we're going to make a strange substitution to make this possible. I'm going to let I'm going to substitute x with a sine theta. In this case, 3 sine theta. Which means dx d theta is what? 3 cosine theta. Which means that dx all by itself is 3 cosine theta d theta. And then I'm going to make a substitution. So this becomes the integral of 1 over square root 9 minus, and instead of x, I'm going to write 3 sine theta. I didn't tell you why. I'm just going to do some magic. I magically came up with it for now, and then I'll tell you after. So I'm just going to show you that it works, and then I'll show you where I came up with it. So 3 sine theta. If I plug 3 sine theta into x squared, what do I get? I'll just write it out. 3 sine theta squared, right? So just replacing my x with a 3 sine theta, then replace my dx with 3 cosine theta d theta. Three sine theta quantity squared, what does that come out to? It's not a trick question. 9 sine squared theta, right? You just square each piece. 3 squared is 9. Sine squared is sine squared. Running out of room here. Okay, so I have 9 minus 9 sine squared. Jumps out at you a little bit that there's a 9 in both places. That's why I chose the 3, right? That's why I chose x would be 3 sine theta. So that when I squared the 3, I'd get a 9, and I'd have 2 9s here. that allows me to kind of factor out a 9, right? So this is going to become the integral of 1 over the square root of 9 times 1 minus sine squared theta. And this is 3 cosine theta d theta. And then I can take that 9 right out of the square root. But actually, I think I won't just yet. I'll leave it for just a minute. One minus sine squared. There should be bells and lights flashing. Cosine squared. Yep. That's the Pythagorean identity. Sine squared plus cosine squared is 1. Right? So if sine squared plus cosine squared is 1, then 1 minus sine squared, just subtract a sine squared from both sides, and you get cosine squared. Okay, so I'm going to replace my 1 minus sine squared with a cosine squared. And then I've got 3 cosine theta d theta. And then I can take the square root of both of these. The square root of 9 is 3. The square root of cosine squared is cosine. So this is the integral of 1 over 3 cosine theta times 3 cosine theta d theta. Oh, that's lovely, right? So this becomes the integral of 1 d theta. What's the antiderivative of 1? Theta, yeah. And then sub back in. Theta was, how is theta related to the original x? Go back. X was 3 sine theta. So what does theta equal? The arc sine of x over 3. Yep. So first, I just have to solve this thing for theta. Divide both sides by 3, then take the arc sine of both sides. The arc sine of x over 3. All right, so the magic that happened here was in the choice of the trig substitution, right? So I let x be 3 sine theta. Oops. So I let x be 3 sine theta. And I also had to substitute for dx, right? But the choice of 3 sine theta was due to the form of the denominator, because I was hoping I could use a trig identity, a Pythagorean trig identity, along with the cancellation to get the dx out of there also. So the 9 is what gave me the 3. I took the square root of it. And then the minus x squared is what tells me sine theta, because I am going to rewrite as a 1 minus sine squared. So here's sort of a general guide. When you're doing trig substitutions, the Pythagorean identities come in handy. So this is 2 of them. And the general guidelines for how to make a substitution: if your integrand contains a radical a squared minus x squared, or just plain old a squared minus x squared, substitute x equals a sine theta. And if the integrand contains a radical a squared plus x squared, or just a squared plus x squared, substitute a tan theta. All right, so let's do one more together. Keeping these guidelines in mind, what should I let t equal? I want to make a trig substitution. What should I make? t equal to? 1 tan theta. Yep, I've got a radical a squared plus t squared, so my a is 1. So t is going to be plain old tan theta, which means dt d theta would be what? Derivative of tangent. Secant squared, thank you. Secant squared theta. And then just multiply both sides by d theta, so I'll be able to replace the dt with something. So I'm solving for dt, so I'll be able to replace it. So I have secant squared theta d theta. All right, so plug in. This is going to become the integral of 1 over t squared times the square root of 1 plus, instead of t squared, I'm going to put in tangent squared, because t is tangent theta. Tangent squared theta. And then dt is secant squared theta d theta. Oh, I probably should have put, instead of I should have replaced this t also. 1 over tangent squared theta times the square root of 1 plus tangent squared theta times secant squared theta d theta. Okay, so now I have a 1 plus tangent squared. What does that simplify to using a Pythagorean identity? Secant squared, right? Tangent squared plus 1 is secant squared. So I have a tangent squared plus 1 under that radical. I'm going to replace it with a secant squared. Times the square root of secant squared. Okay, so the square root of secant squared is plain old secant. So this is the integral of 1 over tangent squared theta secant theta times secant squared theta d theta. One of these secants cancels. So this becomes the integral of secant theta divided by tangent squared theta d theta. All right. Any ideas? Well, the derivative of tangent is secant squared, right? So it's not fully going to cancel with a u substitution. Can you simplify the integrand at all? Rather than before we try to apply some fancy calculus techniques. Maybe we can just simplify that integrand. So I'm going to rewrite both of these trig functions in terms of sine and cosine, the relationship between sine and cosine. How is secant related to sine and cosine? Sine or cosine? It's what? 1 over cosine. And then tangent is sine over cosine. Tangent squared, so I've got sine squared over cosine squared. So this is 1 over cosine theta times cosine squared theta over sine squared theta d theta. So one of my cosines will cancel. So now I have cosine theta over sine squared theta. Ideas? We could try a u sub with sine theta. So the derivative, so that would be a u squared. Yeah, let's try it. So du d theta is going to be cosine theta, which means d theta is du over cosine theta. So then I sub in here, and I'm going to have cosine theta over u squared times d theta, which is du over cosine theta. Hooray! The cosine thetas cancel. Oops, integral. And then this is the integral of u to the -2 du. And use the power rule on that one, right? It's very tempting when you see 1 over something to try to go, oh, ln, right? But that's only if the something underneath is linear, right? It's squared, so I use the power rule. So I have to increase my exponent by 1 and then divide by that -1, which is the same as multiplying by -1. And then I have to replace my u with my sine theta. So this is -1 over sine theta plus c. Oh, we're out of time. Last thing, I have to replace the theta with arctan of t, right? Because t equals tan theta, so theta is arctangent of t. So this is -1 over the sine of the arctan of t, and then that can be simplified further. Okay, I'll just show you. So make a triangle. T equals the tangent of theta. So let's have one of these angles be theta. Tangent is opposite over adjacent, t1. And then this would be the square root of t squared plus 1. So the arctangent of t is theta, right? So maybe I should have just left this as sine theta. And then what's the sine of theta according to that triangle? T opposite over hypotenuse, t over radical t squared plus 1. And then you can simplify that fraction, but that's the answer.